everyone! In this video, we are going to walk through how to implement the selection sort algorithm in JavaScript. We will discuss what selection sort is, how the code works step by step, and also cover big O notation for this algorithm. By the end, you'll understand how selection sort finds and sorts elements in an array. First, let's break down what selection sort does. It is similar to bubble sort in that it sorts the list by finding the next smallest element on each iteration and then placing it in the correct position. The key difference between these algorithms is that instead of swapping elements repeatedly, like bubble sort does, selection sort finds the minimum value in an unsorted part of an array, and then it swaps it just one time. Because selection sort is doing fewer swaps compared to bubble sort, it is a more efficient algorithm. Let's take a look at what this looks like with an actual array. So you see here we have the numbers 29, 10, 14, 37, and 13. What we will do first is start with index 0, so that's number 29, and we will set that as the current minimum. Then we will iterate through the remaining unsorted elements to find out which is the true minimum. So let's step through. The next index is value of 10, and 10 is smaller than 29, so that will become the new minimum. Once we set 10 as the new minimum, we move on to the next item, which is 14. We're going to then check, is 14 smaller than 10? It isn't, so 10 remains the minimum. We move on next to index 3, which is number 37. 37 is also larger than 10, so 10 continues to stay the minimum. That same thing happens with the last element, which is number 13. So after going through the unsorted array, we find that 10 is the minimum. So we will swap minimum 10, which is currently at index 1, with the first unsorted element at index 0. So we make that swap. So there's only one swap. Next, we will iterate again through the array. So now 10 is considered sorted, so that we don't need to touch moving forward. So now we move on to the next index and we set 29 as the new minimum. So now we're starting that comparison to 29. So we look at 29 and 14. 14 is smaller than 29, so now we set 14 to the new minimum. We then compare 14 to 37. 14 stays the minimum. We then compare it to 13, and 13 becomes the new minimum. So we reset that, and then make one swap. So we're going to swap the new minimum of 13 at index 4 with the first unsorted element in index 1, which is 29. So we make that swap. And that continues on. So now 10 and 13 are considered sorted. So you move to the next index, index 2, which is number 14. You set that as the minimum. And then again, you do those last two comparisons. 14 is smaller than 37. It's also smaller than 29. So it is the new minimum. And in this case, there's no swapping because it is in the correct index. So that is sorted. Now let's do this final one. 37 is set to the minimum. We compare that to 29. 29 is smaller, so it's now set to the new minimum. And then again, one swap is performed. So that is now considered sorted. And now the array is completely sorted. Now that we understand how the algorithm works, let's write some pseudocode in here to help guide our code. So the first thing that we want to do is we want to iterate through the list from start to finish. The next thing that we want to do is store the very first element as the minimum value. That will be our starting place so that we have a comparison. Then for each iteration that we go through, if we find a smaller number, we want to set that to the new minimum value. Our next logic would be if the minimum is not the starting index. So if we already have the minimum and it was our first starting place, we won't need to swap anything because it's already in the right spot. However, if it's not in the starting index from that iteration, we will want to swap the smallest element with the first unsorted element. And then we are going to repeat this until the entire list is sorted. Now that we've gone through the pseudocode, I'm clearing my screen here so that we can go through the selection sort algorithm in JavaScript line by line and discuss the thought process behind it. So the first thing that we want to do is declare our function. We're going to call it selection sort, and we will pass in an array called items as the input. This function is going to sort the array in ascending order using the selection sort algorithm. The next thing we want to do is store the length of the array in a variable called length. This will make it easier for us to reference in our for loops later on. So we'll just do const length equals items, which is the name of the array, dot length. Now we want to set up our outer loop, which is going to iterate throughout the entire array. And the outer loop is going to go up to length -1. So let's get that written out here. And you might wonder, so let's review the for loop. We have for let. So we're going to declare this variable as start. Normally you would see something like I here, but start is going to make it more readable for us to know that this is our starting index. We're going to start it at 0. We are going to go from 0 all the way up to length -1, and we're going to continue up one at a time in ascending order. You might be wondering why we're doing length -1. Well, in selection sort, the array is sorted by the time we reach the second to last element. By then, the last element is already in the correct place, so there's no need for the outer loop to go all the way through length. We only need n-1 iterations to sort an array of n items. The next thing, if you remember from our pseudocode, that we want to do is store the first element as the minimum value to start. So inside of this outer loop, we're going to initialize two variables. The first one we're calling min index, and that's going to store the index of the smallest element. And then we will also declare a variable called min val. That's going to store the minimum value. We are initializing these to start, which again will be the first item, the first element index in the array. That will be declared initially as our minimum. Next, again, if you remember from our pseudocode, let me put that here. For each iteration, if a smaller number is found, we want to set that number to the new minimum. So iterations, the key here, we need to create an inner for loop. So we're going to create a new variable that in this case we can title I. And we're going to start I not at 0 because we don't need to compare the same two items. Instead, we want to start at one index above our starting index, wherever that is. For this one, we're going to go all the way through the full length of the array, and we will continue to do that ascending upwards. So for the inner loop, the reason we're using every element in the unsorted portion is because that's the only way to find the true minimum value. If we didn't go all the way up to length, we might miss some of the elements that need to be compared. So we've created our iteration with our for loop. The next thing we need to do is see if there's a smaller number. And if so, looking at our pseudocode, we need to set that number to the new minimum. So let's look at the code for that. We're doing an if statement here. So if the value of the array at I is less than the minimum value, We want to now set the minimum value to I. We also want to then switch the index and set that to I. So for the minimum value, we're doing items at I index. That's the value that we want. And we want to set the index directly to I. This process finds the smallest element in the unsorted portion of the array. So after this inner loop completes, the next thing we want to do is check if the min index is different from start. If it is, we need to swap the elements at start and the min index. So let's put in the pseudocode and code for that. So again, if the minimum is not the starting index from this iteration, we're going to swap the smallest element with the first unsorted element. So let's talk about how this swap works. This line is using an array deconstructing in order to swap the elements. So we have this if statement here. If the value of min index is greater than start, here's where the swapping happens. On the left, we have an array that has the value of start and the value of min index. And on the right side, we're going to swap those two elements. So now we have the value of min index first and start next. So after doing the swap, we want to repeat this until the list is fully sorted, and then we will return our list of items. Now that we have our full solution, let's just walk back through from the top. So we declare a function called selection sort, passing through an array of items. We declare a variable named length with items.length, so we can use that in our for loops below. We start on our outer loop where we have our starting value, our index at 0. We go all the way through length -1 in ascending order. We use this starting index and value to set the minimum index and value. We then have an inner for loop where we start this variable one higher than our starting variable. We iterate through the full length in ascending order. And then we check to see if this item is lower than our current min value. And if it is, we replace both the minimum value and minimum index. The final part of our solution is checking to see if the starting index differs from the minimum index. And if so, we're doing a swap. So we swap the order on the left with the order on the right, and repeat that until we return the fully sorted list of items. Finally, let's talk about the time complexity of selection sort, which we refer to as big O notation. Selection sort has a time complexity of O(n)². But let's talk about what that means and where we're getting that from. So the reason it's O(n)² is there are two nested loops here. We have the outer loop, and it's going to run through n-1 times, and we're talking about n as the number of elements in an array. Then we have the inner loop, and it's going to run n-i times, with I being the current index of the outer loop. So when you multiply the number of iterations in the outer loop by the number of iterations in the inner loop, you get n times n, which is the n² big O notation. And that means that as the size of an array grows, so does the time it takes to sort the array. In fact, it does so what we call quadratically, which means that if we double the size of an array, the sorting process will take roughly 4 times as long. So the larger the array gets, the more time it takes to sort. While selection sort is easy to understand and implement, the time complexity makes it really inefficient for larger data sets. So for large data sets, more advanced algorithms like quicksort or merge sort would be much more efficient. And that is the end of our selection sort solution review.